Hi everyone, today a video on alkenes and specifically looking at the structure, bonding and reactivity. So alkenes are unsaturated hydrocarbons. They don't have the maximum number of CH single bonds they can have. And the double bond makes them much more reactive than alkanes because there's now a high concentration of electrons, a high electron density in this double bond. And alkenes are produced in large quantities when crude oil is thermally cracked. And so we have a general formula for our homologous series of alkenes with one double bond as being CnH2n. Remember that the alkane general formula is CnH2n plus 2. Alkanes are saturated, they have the maximum number of CH bonds. Alkenes unsaturated, we have a CC double bond, which means they don't have the maximum number of CH bonds they can have. Now the simplest alkene is ethene. Obviously if we have a carbon-carbon double bond we need to have at least 2 carbons for that. Then propene for 3 carbons, butene for 4 carbons and so on. And we use the standard IUPAC rules for naming alkenes. So the double bond, we use the suffix "ene" to indicate there's a double bond, and we must number the position of that double bond. And the double bond numbering starts at the carbon that it starts at. So if we have an example of propene, if we had a carbon-carbon double bond and then our CH3 group at the end, that would be prop 1ene, because the double bond has started on the first carbon. Again, also standard IUPAC rules apply in terms of if there's substituents, we have to always make sure that we number them. If we have multiples of them, we use di, tri, etc. And we name things in alphabetical order, not numerical. So, the structure of alkenes. Of course, we have this CC double bond, and the really big difference is, unlike in alkanes, where we have free rotation, the CC bond can rotate in alkanes. In alkenes, there's no rotation around the CC double bond. And you can think of it as the fact that there's now this double bond component kind of locks the bond completely in place. It can't rotate at all. Now, alkenes are trigonal planar. They have trigonal planar carbon atoms with bond angles of roughly 120 degrees. So they're planar molecules. Now for ethene there you can see the actual bond angles of being 180 and 121. The reason why they're slightly different from each other goes back to thinking about the shapes of molecules and the fact that if we have more electrons there's going to be slightly bigger repulsions, and so there's slightly bigger repulsions there around the double bond than there is just between the 2 hydrogen atoms at the end, because there's more electron density, there's that double bond, so slightly more repulsion. And so how do we form this double bond? Well, first of all, we have our single bond framework. Now, single bonds are called sigma bonds. And so we have our single bonded framework. We have a carbon-carbon single bond in the middle, and we have a carbon-hydrogen single bonds, 4 lots of carbon-hydrogen single bonds. Now, you don't have to know too much about the actual orbital naming of all this, but how these actually form is essentially these are called sp2 orbitals on the carbon. Just think of them as the orbitals on carbon. And so when we make a CH bond, we have this orbital on the carbon overlapping with a 1s orbital of the hydrogen. And we have 2 of these carbon orbitals overlapping to form this sigma CC bond. Then we form the double bond component. And the double bond component is called a pi bond. And it's formed by 2 p orbitals overlapping. So on our carbon atom, the way that this is sort of configured in terms of the orbitals is that there will be 1 p orbital that is left with 1 electron in that's unpaired and not used up in the single bonded framework. And so if we have that, these p orbitals can kind of communicate and combine to produce a pi orbital. And so you can see at the top right here that you have those 2 localized p orbitals, and actually the pi orbital is kind of smeared out across both of those carbon atoms. The key thing is, though, that it's the p orbital contribution that makes the double bond. There's 1 free p orbital per carbon atom that has 1 electron in each that can overlap. And so generally the overall structure of our alkene is we have our CH single or our sigma bonds. We have a CC single bond, which has a bond enthalpy of 346 kilojoules per mole. We then have our pi bond, double CC bond, pi bond, which is 256 kilojoules per mole. And so the total for this alkene of the sigma bond and the pi bond makes an alkene CC up to be 602 kilojoules per mole. So there's this slight kind of discrepancy here that an alkene is a much stronger CC bond than an alkane, but it's also much more reactive. It's something that we call thermodynamic stability versus the kinetic reactivity of this molecule. You'll also notice that the bond density for the double bond part of it is not exactly the same amount as the single bond. You'd expect potentially that, okay, it's a double bond rather than a single bond, so it's just twice the amount of the single bond, and you'll see that the double bond actually is slightly less. The reason for that is because the p orbitals actually overlap slightly less well than the sp2 orbitals and the 1s orbitals on the carbon and the hydrogen respectively. So the orbital overlap is just slightly less good. So we can now look into the types of isomers that we can get in alkenes. Remember that our isomers have the same overall formula, but the connectivity of the atoms for these structural isomers, the connectivity of the atoms is different. And so as well as chain and functional group isomers that we had in alkanes, alkenes can form two types of isomers that involve the double bond specifically. Now the first is a type of structural isomerism where the atom connectivity actually differs. And this is a type called position isomerization. This is where the double bond is literally in a different position between different carbon atoms in the molecule. So the example here is butyene versus butanene. So note the naming of it. We look for our longest carbon chain. For both of them it's 4 carbons long. We have an alkene, double bond, so we end with the suffix -ene, and then we have to number where that double bond is. For the example on the right, it starts at carbon number 1. For the example on the left, it starts at carbon number 2. Remember, we always want the lowest number possible when we number these things. So we have butyene and butanene. So really note that the number is the carbon atom where the double bond starts. But you can see that the double bond is at carbon number 1 or at carbon number 2. It's moved the position in the molecule. So that's a position isomer. The other type of isomerization is called geometric isomerization, and it's a form of what we call stereoisomerism. So stereoisomerism is where we have isomers that have the same structural formula, i.e. the atoms are all connected in the same way, but the bonds are arranged differently in space. They have different 3D arrangements. And so the type of geometric isomerism we're looking at here is EZ isomerization. And it's all based on the atomic numbers and the atomic weights of the groups that are attached to our alkene. So what we want to do is we want to look for the 2 heaviest groups that are attached to our alkene. And then we want to see, are they above or below the double bond? If we draw a line straight through that double bond, are they above or below it? So if we look at the butyene example, we have an example where we have our CC bond in the middle, and then we have our 2 CH3 groups being both below that double bond. Now, if we looked at that molecule, we have to look for the 2 heaviest groups. The 2 heaviest groups there are clearly the CH3 over the hydrogens. So those are the 2 we're interested in. Those are the 2 that I've highlighted red. Alternatively, I could have one of those methyl groups being below and one of those methyl groups being above. And so this is where the E and Z notation comes in. If both of the groups are on the same side of the double bond, i.e. they're both below or they're both above, this is called Z. So this is Z butyene. If they are opposite sides, if one is above and one is below, it's called E. So the bottom example is E butyene. Now you may also see cis and trans being used. That's the older notation for E and Z. The actual technical IUPAC way to name them now, and the way that you should name them in the exam, is E and Z. So Z means they're on the same side of the double bond, E means they're on the opposite sides of the double bond. For some molecules, EZ isomerization is just not possible. So for example, butanene, the reason is because we have to look for our heavy groups. Well, here there's only one heavy group. There's the CH2CH3 group, and then 3 hydrogen atoms. And so we can't have EZ isomerization, that's just named as butanene. And this leads to a more general rule that if we have 2 of the same group attached to the same carbon, we can't have EZ isomerization. So you'll see the 2 hydrogen atoms that I've highlighted blue. That's 2 of the same group, 2 hydrogen atoms that are bonded to the same carbon. And if we see that, we can't have EZ isomerization. And so the reason why these are isomers of each other is because we said there's no rotation around that double bond. So if you look at Z-butene and E-butene, you might think that, oh, that's very easy to interconvert between the two because we can rotate one of the carbon atoms around. In an alkane, yes, you can. In an alkene, no, you can't, because that double bond has kind of locked the molecule so much, made it so rigid, that it can't, there's no free rotation. So in terms of physical properties, the double bond doesn't really affect physical properties such as boiling points and melting points. Like alkanes, the van der Waals forces are the only intermolecular force that acts between the alkene molecules. And so like alkanes, they have pretty low melting and boiling points, and those melting and boiling points increase with increasing chain length, because increasing chain length means more electrons and therefore stronger van der Waals forces. And alkenes generally are not soluble in water because they're based on non-polar carbon and hydrogen bonds. However, in terms of chemical properties, the double bond makes a really big difference in terms of reactivity. As I said a couple of slides ago, we have a much stronger CC bond, but alkenes are much more reactive than alkanes. And the reason is because we have this really electron-rich, electron-dense area between those two carbon atoms where the double bond is. And this can be easily attacked by electron-deficient species, something that we call electrophiles. And the technical definition is an electrophile is an electron pair acceptor. Typically, it's a molecule or an ion that is electron deficient or positively charged. And since alkenes are unsaturated, they undergo something called addition reactions. We add to the double bond. We add across the double bond to make a saturated molecule. So, time to have a go at some questions. So the first is to name the following alkenes and then to draw out the 6 isomers of pentene. So if you'd like to have a go, pause the video and the answers will be on the next slide. So the first question was to name the following alkenes. Now I've drawn these out as skeletal formula. You could have drawn them out as the displayed formula, however works for you. It's good to always have the ability to interconvert between the two. So the first example, the first thing to always do is to find our longest carbon chain. Our longest carbon chain here is 6 carbons long, so it's based off a hexyl length chain. We have a double bond, so we're going to be using the suffix -ene. We also have a bromine substituent, and we have a methyl group substituent that's not part of our main chain. Now again, we need to aim for the lowest possible numbering, so we can number from left to right, or we can number from right to left. The lowest possible numbers we get from doing that is if we go from left to right. And so our alkene, our double bond, starts at carbon atom number 2. So it's going to be a 2-ene. It's based off 6, so the ending of that becomes hex 2-ene. And then we just have to note where our substituents are. So there's a methyl group on 2, a bromo group on 4, but remember that we name alphabetically, not numerically. So it is 4-bromo, 2-methyl, hex 2-ene. The second example here is an alkene a molecule where we've got 2 alkene double bonds here. So we're going to have diene, di for 2 of them, diene somewhere at the end. And again, our longest carbon chain is 6 carbons long. So again, it's based off a hexyl group. Then we have no other substituents. So the name of this could be named as either 2,4-hexadiene or hexa-2,4-diene. So note how we've numbered both double bonds. So we have 2, 4, and we have the diene. And the second question was to draw the 6 isomers of pentene. Now the way that I go about doing these kind of questions normally is to first think about the really simple types of isomerization. So is there a position isomer that I can draw? And in the case of pentene, well, yes, there is. We can start by drawing the sort of simplest one, pent-1-ene, double bond right at the start, and then just a straight chain alkyl group off one of the carbon atoms. Or I can move the double bond and make pent-2-ene. I can't make pent-3-ene because we'd then have to just count from the other end of the chain, and that would end up being pent-2-ene as well. So position isomers, we have pent-1-ene and pent-2-ene. Then we can start to think about chain isomers as well. So for pent-1-ene, I can start to change the alkyl chain I have, the CH2, CH2, CH3, I can start to mess about with that chain. And so the example that ends up leading to is the one on the bottom right, 3-methyl-butanene. So in this case, what's happened here is I've branched that chain. The longest carbon chain now becomes 4 carbons long with a methyl group on the 3 position. I can also, rather than having a long chain CH2, CH2, CH3, I can break that chain up and have CH2, CH3 for one of the bonds and CH3 for another one of the bonds. And so this gives the top right example of 2-methyl-butanene. Again, our longest chain is now 2 carbons long, and we've just moved essentially we've moved our methyl group. It's kind of a position isomer of that 2-methyl rather than 3-methyl. Then we can also have another one, which is 2-methyl-butene. So this again essentially is another, rather than having CH2, CH2, CH3, break it up into 3 lots of CH3, double bond in the middle. Our longest chain is now still 4 carbons long, but it's now 2-methyl-butene. You could also consider that to be a position isomer of 2-methyl-butanene. So all of these are quite often related to each other, so I tend to start by writing out simple ones and then thinking, okay, it's a position isomer of this one, can I do any chain isomers of that? Once we've gone through all of those, and those are all of the structural isomers, we can then start to think about our stereoisomers. And remember that the type of stereoisomerism we're looking at is geometrical isomerization, our EZ isomerization. Now for pentanene, the 2-methyl-butene, the 2-methyl-butanene, and the 3-methyl-butanene, EZ isomerization is just not possible because we have 2 of the same group attached to one of the carbons. For most of them, it's 2 hydrogens attached to the same carbon. For the 2-methyl-butene, it's 2 CH3 groups attached to the same carbon. So we can't have EZ isomerization. However, the pentanene cases, we can look for our 2 heaviest groups. Remember that EZ isomerization looks at the atomic weights of the things that are attached. So our 2 heaviest groups here are the CH3 group and the CH2 CH3 group. And these can either be both above or below to give Z pentanene, or one above and one below to give E pentanene. And those are the 6 isomers. So thank you for watching. You can find lots more videos like this on my YouTube channel. If you found this helpful, please consider leaving a review on one of the tuition websites. I offer online tuition for chemistry, so if you're interested in that, please contact me on my tuition pages for prices and details of how to contact me. And if you need any more help with your chemistry, feel free to drop me an email. I'm always happy to help.